Welcome to this explainer. Today we're doing something a bit different. We're not just going to sit here and memorize chemical reactions. Nope, we're going to deconstruct one of the most fundamental processes in organic chemistry, and we're looking at it through a totally different lens. Think of it less like a dry formula on a chalkboard and way more like a highly logical, meticulously planned molecular heist. We're looking at nucleophilic addition to a carbonyl group. By understanding the precise vulnerabilities of our target and the exact sequence of the breach, you'll be able to predict the outcome of countless reactions without any brute force memorization. Let's get right into it.
Here's our blueprint for today. First, we'll meet the carbonyl target. Then we'll break down the three-step attack mechanism. After that, we'll compare the reactivity of aldehydes versus ketones, and finally, we'll check out the aromatic ring shield.
All right, Section 1, meet the carbonyl target. Casing the joint, because every successful heist starts by understanding exactly where your target is vulnerable. To pull off this chemical breach, we need to know exactly what we're aiming at. Our target here is the polar carbonyl group. Basically, this is a carbon atom double bonded to an oxygen atom. But the real vulnerability, that lies in the electron imbalance. See, oxygen is highly electronegative. It's a total electron hog. It pulls the shared electrons in that double bond right toward itself. And this creates a very distinct polarization. You get a partial negative charge on the oxygen and, critically, a partial positive charge on the carbon. In the world of molecular attacks, that partial positive charge is basically a glowing neon sign painting a massive target right on the carbon's back. It is literally begging for an incoming molecule rich in electrons to come and strike. Now, what's really fascinating about this setup is the physical geometry. It's not just about the electronic charge, right? It's about the physical space. The carbonyl carbon and the three atoms attached to it are sp2 hybridized. What that means in practical terms is that they all lie completely flat in exactly the same plane. Think of it like a pancake. Because it's entirely flat, there's absolutely no structural debris above or below it to get in the way. It leaves this wide open, totally unobstructed path of attack for incoming nucleophiles. Those electron-rich attackers hunting for a positive target. Moving right along to Section 2, the three-step attack mechanism. Executing the breach. Okay, let's dive into this. We know our target, we see the opening, so let's execute the infiltration. The whole event plays out in three distinct, highly choreographed phases. Step 1 is the initial nucleophilic attack. Step 2 is a pretty dramatic hybridization change. And Step 3 is the proton capture. Let's break down exactly how this sequence actually happens. Phase 1 is the breach. Our attacker, the nucleophile labeled nu with a negative charge, makes its big move. Because of that flat sp2 geometry we just talked about, the nucleophile doesn't just wander in from the side where it bumps into a bunch of other atoms. No, it strikes the electrophilic carbon exactly perpendicular to the flat plane of those sp2 orbitals. It drops in right from the top, directly hitting that vulnerable partial positive charge. The very second the nucleophile makes contact and bonds to the carbon, we trigger phase 2. The target molecule just can't stay flat anymore. As the new bond forms, the electrons from that carbon-oxygen double bond are forced entirely up onto the oxygen atom. This triggers a massive structural shift. The carbon fundamentally changes its geometry from that flat sp2 hybridization to sp3, popping up into a 3D pyramid shape. We call this a tetrahedral alkoxide intermediate. It's this critical midway point where it's holding a full negative charge on the oxygen. But of course, that intermediate is super reactive and unstable. I mean, the heist isn't really over until the molecule is neutralized, right? So in phase 3, this negatively charged intermediate reaches out into the surrounding reaction medium and captures a proton, an H+ ion. The oxygen bonds with this proton, completely neutralizing the overall charge of the molecule and producing a stable, electrically neutral addition product. And just like that, the breach is complete. The target has been permanently altered.
Let's move to Section 3, aldehydes versus ketones reactivity, assessing the defenses. Let's see how this builds onto our whole concept of molecular security, because not all carbonyls are sitting ducks here. Some definitely have built-in defenses.
When we compare aldehydes and ketones, we quickly find that aldehydes generally undergo nucleophilic addition a lot more readily. They're just easier targets. Ketones, on the other hand, put up a much better fight. And this difference in reactivity basically comes down to two primary defense mechanisms: physical bulk, which is known as the steric factor, and electronic shielding, known as the electronic factor. And this brilliantly illustrates that first defense mechanism, the steric factor. Consider how this works. An aldehyde only has one alkyl group, represented by the green circle labeled R. The other side is just a tiny little hydrogen atom, leaving the carbon largely exposed and totally open to attack. But then look at the ketone. The ketone is flanked by two relatively large, bulky alkyl substituents. These two R groups basically act like massive physical bouncers, standing on either side of the target carbon. They physically crowd the space, hindering the approach of the incoming nucleophile and making it significantly harder to actually land a successful strike. Then we have the second layer of defense, which is invisible but honestly incredibly powerful, the electronic factor. Alkyl groups aren't just physically large, they're also electron-donating. Because ketones have two of these electron-donating alkyl groups, they are constantly pushing electron density toward that central carbonyl carbon. Remember how we said that partial positive charge was the glowing neon target? Well, by pushing electrons toward it, those two alkyl groups effectively satisfy a lot of that positive charge. They reduce the electrophilicity of the carbon, essentially dimming the brightness of that neon sign. With a much lower positive character, the ketone is simply a far less enticing target for an attacker compared to an aldehyde which only has one alkyl group providing that electronic shield. All right, on to section 4, the aromatic ring shield, the ultimate bodyguard. We've seen the basic physical and electronic defenses, but now let's look at a molecule that employs some seriously heavy-duty advanced security. Meet benzaldehyde. This molecule attaches the vulnerable carbonyl group directly to a benzene ring. Now, this is not just your ordinary R group. It's an aromatic ring, which means it has this circulating cloud of electrons. Benzaldehyde uses a phenomenon called resonance. The benzene ring actively participates in sharing its electron density directly with the carbonyl carbon. It is a highly efficient system that drastically reduces the electrophilicity of the target carbon, shielding it from attack way more effectively than a standard alkyl group ever could.
So, the crucial point is this. If you compare benzaldehyde to a standard non-aromatic aldehyde like propanal, benzaldehyde is noticeably less reactive. Even though it is structurally an aldehyde, its specialized resonance security system just makes it a much tougher target to breach. That aromatic ring acts as an active electronic bodyguard, constantly neutralizing the vulnerability at the core of the carbonyl group.
Let's quickly summarize what we've uncovered in this explainer. The success of our molecular heist depends entirely on 3 key defenses. First up, steric hindrance, the physical blocking by bulky alkyl groups that literally crowd out the attackers. Second, electronic effects, the electron donation from those same groups that dials down the target's positive charge. And third, aromatic resonance, the advanced shielding system that actively dampens the carbon's vulnerability. If you can evaluate these 3 factors, you seriously don't even need to memorize a list of reactive molecules. You can just look at a structure and immediately deduce exactly how vulnerable it is to a nucleophilic addition. Which brings us to a really fascinating frontier to close on. We've seen how nature and basic chemistry use physical bulk and electron clouds to slow down an attack. But think about the real-world engineering of molecules for a second. If you were a chemist tasked with designing a new drug or a novel material, and you needed a carbonyl group to be absolutely 100% immune to nucleophilic addition, how would you design it? What kind of extreme steric or electronic architecture would you have to build to create an unbreakable molecular vault? It's a question that really pushes the boundaries of molecular design, and it's one I'll leave you to ponder. Thank you so much for joining me on this explainer. Keep questioning and keep exploring.